Hello everyone. This is an audio recorded lecture for visually impaired students on the topic Diazonium salts from organic chemistry. So let's start it. Introduction. Arene diazonium salts were discovered by John Peter Grace in 1858. They have the general formula Ar N2 positive X negative, where Ar stands for the aryl group and X may be any anion such as chlorine, bromine, nitro, HSO4 negative, BF4 negative, etc. Aliphatic diazonium salts are also known, but they are highly unstable. They rapidly decompose even at low temperatures, forming carbocations and nitrogen gas. Therefore, in this unit, we shall discuss the chemistry and synthetic applications of arene diazonium salts only, particularly with reference to benzene diazonium chloride. Nomenclature. Diazonium salts are named by adding the suffix diazonium to the name of the aromatic compound followed by the name of the anion. Some examples are benzene diazonium chloride, para-toluene diazonium hydrogen sulfate, para-nitrobenzene diazonium fluoroborate, and para-chlorobenzene diazonium bromide. Next is structure of benzene diazonium chloride. Molecular formula of benzene diazonium chloride is C6H5N2Cl. The molecular formula of benzene diazonium chloride is C6H5N2Cl. Next is Grease structure. Grease proposed structure for diazonium chloride in which both the nitrogen atoms were directly linked to the benzene molecules. This structure, however, failed to account for the following facts. First is its salt-like character. Second is displacement of both the nitrogen atoms by a univalent atom or group in most of its reaction. Next is its reduction to phenyltrazine, in which only one nitrogen is attached to the benzene ring. Next is formation of azo compounds by coupling reaction. Next one is formation of aromatic diazonium salts from penta-substituted anilines. Next is Kekulé structure. Kekulé proposed a structure for benzene diazonium chloride in which only one nitrogen was linked to the benzene nucleus. Evidence in favor of Kekulé structure given by Kekulé explain most of the drawbacks of grease structure, such as reduction to phenylhydrazine, formation of azo compounds by coupling reaction, preparation of diazonium chloride salt from penta-substituted aniline, and displacement of both the nitrogen atom by a univalent atom. Points against Kekulé structures are that it could not explain its salt-like character and ion stability as compared to azo compounds, since both contain nitrogen-nitrogen double bond. Next structure is Blomstrand structure. Blomstrand suggested structure for the benzene diazonium chloride in which the nitrogen attached to the benzene ring is pentavalent while the other one is trivalent. Evidence in support are it explains all the objection of structure first and second. This structure is further supported by the following fact. First is its ready solubility in water but not in common organic solvent. Second is its complete ionization as shown by conductivity measurement. Next is the presence of a triple bond as shown by infrared spectroscopy. Next is its instability as compared to azo compound. And next is it explains the geometrical isomerism as shown by diazotates or diazodates, which are metallic salts of diazonium hydrochloride. The sodium benzene diazotate can exist as a pair of geometrical isomers due to hindered rotation about the N double bond N. Next is preparation of diazonium salt. Aromatic diazonium salts are generally prepared by adding a cold aqueous solution of sodium nitrite to the solution or suspension of a primary aromatic amine in an acid at 273 to 278 Kelvin temperature. For example, when C6H5NH2 react with NaNO2 in the presence of HCl at 273 Kelvin temperature, then benzene diazonium chloride is formed and NaCl and water are obtained as substituted product. Diazonium salts are also formed when aromatic primary amines react with the nitrite esters. Diazonium salts are also formed when aromatic primary amines react with the nitride esters such as amyl nitrite. The nitrite esters needed for the purpose are prepared by treatment of alcohols with nitrous acid. This process of conversion of a primary aromatic amine into its diazonium salt is called diazotization. Next, general procedure for diazotization. The primary aromatic amine is dissolved or suspended in a dilute acid such as HCl, H2SO4, etc. Three molecules of the acid are generally used for every mole of the amine to be diazotized. 1 mole to form the salt of the amine, 1 mole to liberate nitrous acid from sodium nitrite, and 1 mole to keep the reaction mixture acidic enough to suppress the undesirable side reaction such as coupling of the diazonium salt thus formed with the free amine. The amine solution is cooled and a cold aqueous solution of sodium nitrite is added slowly to it at such a rate that the temperature of the reaction mixture does not rise above 278 Kelvin. The addition of sodium nitrite solution is stopped as soon as a few drops of the reaction mixture produces a blue color with starch potassium iodide paper showing the presence of unreacted nitrous acid in the reaction mixture. Too much excess of nitrous acid is generally avoided since it subsequently interferes with the reaction of diazonium salt. The excess of nitrous acid may be destroyed by the addition of urea. Since diazonium salt slowly decompose even at low temperature, they are used immediately after preparation. So here is the mechanism given for the diazotization reaction. And this is the procedure here. Next is evidence in support for the diazotization reaction. This mechanism is supported by the observation that aromatic amines containing electron withdrawing groups such as NO2 are less easily to diazotize. This is due to the reason that the nucleophilicity of the amine group is reduced due to the electron withdrawing effect of the NO2 group as shown here. Conversely, aromatic amines containing electron donating groups at ortho and para positions undergo diazotization much more rarely than aniline. Next topic is stability of diazonium salt. Aromatic diazonium salt are much more stable than aliphatic diazonium salt due to the dispersal of the positive charge over the benzene ring as shown below. So these are the structures explaining dispersal of positive charge over benzene ring. Alternatively, the instability of diazonium salt is due to their tendency to eliminate an exceptionally stable molecule of nitrogen to form carbocation. This is the mechanism given here. Okay, since the phenyl carbocation is much less stable than alkyl carbocation, therefore aromatic diazonium salt have much lower tendency to eliminate nitrogen than aliphatic diazonium salts. In other words, aromatic diazonium salts are much more stable than aliphatic diazonium salt. Repeating this again, aromatic diazonium salts are much more stable than aliphatic diazonium salts. Next is physical properties of diazonium salt. Arene diazonium salts are generally colorless crystalline solid and highly soluble in water. Many diazonium salts, especially nitrites, are dangerously explosive in the dry state. Therefore, they are never isolated but are usually prepared in situ and used immediately after their preparation. However, certain diazonium salts as fluoroborates are relatively insoluble in water and are stable enough to be dried and stored. Some diazonium salts also form complexes with metallic salt such as zinc chloride. These complexes are generally insoluble. Next is chemical properties of diazonium salt. Arene diazonium salts are highly reactive compounds. Their high reactivity arises due to the excellent leaving ability of the diazo group as a nitrogen gas N2. They are therefore extremely useful synthetic reagent in organic chemistry. The reaction of diazonium salts are broadly divided into two categories. First, reaction in which the diazo group is replaced by monovalent atoms or groups. Second is reaction in which the nitrogen atoms are retained. So, firstly, we study the reactions in which the diazo group is replaced by monovalent atoms or groups. Some important reaction of this category along with their synthetic applications are discussed below. First is replacement by hydrogen, which is also known as deamination. The replacement of the diazo group by hydrogen or the reduction of diazonium salt to arenes is usually brought about by treating a diazonium salt with hypophosphorus, that is H3PO2 acid, at room temperature, preferably in presence of Cu first salt as a catalyst. This is the reaction here. This reaction can also be carried out by treating amines with sodium nitrite and hypophosphorus acid as diazotizing reagent. Alternatively, diazo group may be replaced by hydrogen by heating arene diazonium salts with ethanol. This whole process involving the diazotization of an amine followed by reduction of the diazonium salt or replacement of the diazo group by hydrogen is called deamination. It may be emphasized here that during the reaction of diazonium salt with ethanol, two products are usually obtained. One involving the replacement of the diazo group by hydrogen as discussed above, and the other by the ethoxy group. When phenol react in the presence of ethanol, it gives benzene diazonium chloride. When it further react with ethanol, it gives benzene plus CH3CHO plus nitrogen gas and hydrogen chloric acid. The relative amount of the two products, however, depend upon the nature of the diazo compound and the alcohol used. If one group is present in the nucleus and ethanol is used, the replacement of diazo group by hydrogen predominates. If on the other hand methanol is used, the predominant product is aryl methyl ether, that is anisole. Here is the mechanism given for this reaction. This is the mechanism. Next is synthetic application. The importance of deamination is illustrated by the following application. First is synthesis of metabromotoluene. When para-toluidine react with pyridine, then acylation occurs and paramethyl acetanilide form. When it further react with Br2CH3COOH, that is when it undergo bromination, then 2-bromo-4-methyl analide is formed, which is further when react with H2SO4, that is hydrolysis, it gives 2-bromo-4-methyl aniline, which when further react with NaNO2 over HCl at 273 Kelvin temperature, that is when it undergo diazotization, then benzene CH3 metabromine para N2Cl2 forms. When deamination occurs here, then finally metabromotoluene is obtained. Recall, metabromotoluene cannot be prepared by direct bromination of toluene or Friedel-Crafts alkylation or bromobenzene due to ortho-para directing nature of the methyl group and the bromine atom. Second, synthesis of 1,3,5-tribromobenzene or symmetric tribromobenzene. When alanine undergo bromination, then 2,4,6-tribromoaniline form. When it further undergo diazotization in the presence of NaNO2 over HCl in between the temperature 273 to 278 Kelvin, then 2,4,6-tribromo diazonium chloride formed, when further undergo deamination, then 1,3,5-tribromobenzene forms. Third is synthesis of 3,5-dibromotoluene. When para-toluidine undergo bromination, then 2,6-dibromo-4-methyl aniline forms, when it further undergo diazotization, then benzene attached N2HSO4 and 2-bromine CH3. When this uh, further undergo deamination, then 3,5-dibromotoluene form. Recall, direct bromination of toluene with bromine FeBr2 gives 2,4-dibromotoluene. Second is replacement by hydroxyl group, that is a synthesis of phenol. Diazonium salt react with water in presence of acid to form phenol. The reaction is generally carried out by adding the solution of a diazonium salt to a large volume of boiling dilute sulfuric acid. The acidic condition minimizes the side reaction involving the coupling of phenol with diazonium salt. Mechanism. This reaction occurs by SN1 mechanism as shown below. Next is synthetic application. This reaction is especially important since only a few methods are available for the direct introduction of a hydroxyl group into the benzene nucleus. Synthesis of meta-nitrophenol. Meta-nitroaniline undergo diazotization. Further, a product formed which, when react with dilute H2SO4, gives meta-nitrophenol. Third is replacement by halogens. Different methods are used depending upon the halogen to be introduced. First is replacement by chlorine or bromine, that is Sandmeyer reaction. Aryl chloride and bromide can be easily prepared by treating a freshly prepared cold aqueous solution of an arene diazonium salt with a solution of cuprous chloride in hydrochloric acid or cuprous bromide in hydrobromic acid. This reaction is known as Sandmeyer reaction and give aryl halide in 60 to 80% yield. This is the reaction here. When benzene diazonium halide react with CuBr over HBr, then aryl bromide, nitrogen gas and halogen is formed. But when benzene diazonium halide react with CuCl over HCl, then aryl chloride plus nitrogen gas and halogen is obtained. Here are the example given. It may be noted here that it is the halogen which is attached to copper which enter the nucleus. Next is mechanism of Sandmeyer reaction is believed to occur by a free radical pathway as delineated below. When CuCl react with HCl, then CuCl2 negative and H positive ions are obtained. This is the reaction further. Next is Guterman reaction. It is a modification of the Sandmeyer reaction in which copper powder and a hydrogen halide are used instead of cuprous halide dissolved in the corresponding hydrogen halide. Yields are often lower, that is around 40%, than those obtained by Sandmeyer reaction. Synthetic application. Synthesis of 1,2,3-tribromobenzene. When para-nitroaniline undergo bromination, then 2,6-dibromo-4-nitroaniline is obtained, which when further undergo diazotization, then a product is formed, which when further undergo Sandmeyer reaction, then 3,4,5-tribromo-nitrobenzene is obtained, which when further react with SN over HCl or NaNO2 over HCl, then 3,4,5-tribromobenzene diazonium chloride is obtained, which when further undergo deamination, then finally 1,2,3-tribromobenzene is obtained. Next is replacement of iodine. The replacement of the diazo group by iodine does not require cuprous halide or cuprous as catalyst. It is simply achieved by treating diazonium salt with potassium iodide or a solution of iodine in potassium iodide. Third is replacement of fluorine, that is Balz-Scheinman reaction. When an aqueous solution of a diazonium salt is treated with fluoroboric acid, that is HBF4, diazonium fluoroborate gets precipitated. It is filtered and dried. Unlike other diazonium salt, diazonium fluoroborate are fairly stable compound. When dry diazonium fluoroborate is heated, it decomposes to produce aryl fluoride and boron trifluoride. Here are the example given for Bals-Scheinman reactions. And also the mechanism of Bals-Scheinman reaction is given here. Next is synthetic application for synthesis of fluorobenzene. When aniline react with NaNO2 over HCl at 273 to 278 Kelvin temperature, then diazonium chloride is obtained, which when further react with HBF4, then benzene diazonium fluoroborate is obtained, which on heating gives fluorobenzene plus BF3 plus nitrogen gas. Next is replacement by the cyano group for synthesis of nitriles. Aryl nitrile can be prepared by treating a diazonium salt with cuprous cyanide or potassium cyanide and copper powder. To avoid the loss of cyanide as HCN, the diazonium salt solution is first neutralized with sodium carbonate and then treated with cuprous cyanide. This reaction is called modified Sandemeyer reaction. Next is synthetic application. Since hydrolysis of nitrile give carboxylic acid, therefore synthesis of nitrile provide us with an excellent method for the preparation of carboxylic acid from nitro compounds. For example, when toluene undergo nitration, we obtained paranitrotoluene, which on reduction give paratoluidine, which when further undergo diazotization give benzene diazonium chloride, which when further undergo neutralization with Na2CO3 and CuCN gives paratoluene nitrile, which when finally undergo hydrolysis gives paratolic acid. This is the whole reaction. Okay, next is replacement by nitro group. Nitro compounds are generally prepared by treating an arene diazonium fluoroborate with an aqueous solution of sodium nitrite in the presence of copper powder. That is, when benzene diazonium chloride react with HBF4, it gives benzene diazonium fluoroborate, which when further react with NaNO2 and Cu gives nitrobenzene plus nitrogen plus NaBF4. Next is replacement by an arsenic acid, that is ASO3H2 group, which is also known as Balt reaction. Treatment of an arene diazonium salt with sodium arsenite in presence of copper sulfate followed by acidification gives an arylosonic acid. For example, when benzene diazonium chloride react with Na3ASO3 in the presence of CuSO4, it gives C6H5ASO3Na2 plus NaCl plus nitrogen gas is liberated, which when further react with 2 moles of HCl gives phenyl arsenic acid and NaCl. Next is replacement by an aryl group, that is Gomberg-Beckmann reaction. When an arene diazonium salt is treated with an aromatic compound, that is liquid or its solution in an inert solvent if solid, in presence of an aqueous alkali, biaryl are formed. Yields are usually less than 40%. For example, when parabromobenzene diazonium chloride react with C6H6 in the presence of NaOH, then parabromodiphenyl is obtained, and the yield of parabromodiphenyl is 35% here. Mechanism of this reaction is, the reaction is believed to occur by free radical mechanism in alkaline medium. Diazonium salts are converted into the corresponding azo compound which decompose to produce aryl radicals. B. Reaction in which nitrogen is retained. तो अभी हमने क्या पढ़े थे, जिसमें जो हमारा बेंजीन डाइजोनियम क्लोराइड है उसको रिप्लेस किया जाता है बाय अ स्मॉल एटम या फिर ग्रुप. अब हम क्या पढ़ रहे हैं, वो रिएक्शन जिसमें कि नाइट्रोजन को रिटेन किया जाता है. तो उसमें हमारा फर्स्ट आता है रिडक्शन टू एराइल हाइड्राजाइंस. अरीन डाइजोनियम सोल्ट अपॉन रिडक्शन गिव गुड यील्ड्स ऑफ अराइल हाइड्राजेंस. This reduction can be brought about by a number of reagents such as stannous chloride, hydrochloric acid, sodium sulfite, hydrosulfite, and even electrolytically. If, however, strong reducing agent such as Zn over HCl is used, the product is an aromatic amine. For example, when benzene diazonium chloride react with Zn over HCl, it gives phenylhydrazine, which when further react with Zn over HCl, it gives aniline and ammonia. Next is mechanism of reduction of diazonium salt with sodium sulfite. The reaction probably occurs through nucleophilic attack by the sulfur atom of the sulfite ion on both the nitrogen atoms, forming the dianion of hydrazine sulfonic acid, which is then converted into hydrazine in presence of an acid. This is the mechanism here. Okay, so next है coupling reaction. Arene diazonium salt react with highly reactive aromatic compound such as phenol and amine to form brightly colored azo compounds. This reaction is known as coupling reaction and is extensively used in azo dye industry, whereas coupling with phenols occur in basic medium, that of amines occurs in the phenately acidic medium in between 273 to 278 Kelvin temperature. For example, when benzene diazonium chloride react with phenol in basic medium at 273 to 278 Kelvin temperature, then phenyl hydroxyazobenzene is obtained. And when benzene diazonium chloride react with aniline in basic medium, it gives diazoaminobenzene, which on rearrangement gives para-aminoazobenzene. Coupling usually occur at para position with respect to OH or NH2 group. If, however, the position is blocked, it occurs at the ortho position. For example, when benzene diazonium chloride react with paracresol in basic medium, it gives 2-phenylazo 4-methylphenol. If a compound contain both an amino group as well as an hydroxyl group at para position with respect to each other, then the orientation of the coupling reaction can be changed by changing the pH of the medium. For example, when para-aminophenol react with benzene diazonium chloride in basic medium, it gives 4-amino-2-phenylazophenol. And when para-aminophenol react with benzene diazonium chloride in acidic medium, it gives 4-amino-3-phenylazophenol. The well-known indicator methyl orange, which is widely used in acid-base titration, is obtained by coupling the diazonium salt of sulfonylic acid with N,N-dimethyl-aniline. Here are some reaction givens. Next is mechanism of coupling reaction. The coupling reaction between benzene diazonium chloride and phenols or amines is an example of electrophilic substitution reaction in which diazonium ion act as the electrophile while phenol or amine act as a nucleophile. A. Coupling with phenols. Since benzene diazonium ions are only weakly electrophilic, therefore strong nucleophiles are needed for the reaction to occur. Further, since phenol is weakly nucleophilic but phenoxide ion is strongly nucleophilic, therefore coupling reaction of phenols are usually carried out in alkaline medium. Role of pH. The pH of the medium play an important role in the coupling of phenols. As stated above, coupling of phenol is carried out in the weakly basic medium as explained above. In the alkaline medium, the diazonium salt first forms diazonium hydroxide, which immediately rearranges to diazohydroxide, which further react with alkali to form the corresponding salt called the diazotate. All these three species in fact exist in equilibrium. Since at high concentration of OH negative ions, the equilibrium will shift in favor of diazohydroxide and diazotate, both of which do not couple. Therefore, for the desired coupling reaction to occur, the pH must be kept as low as possible in the alkaline medium. However, a too low pH would suppress the dissociation of phenol to phenoxide ion. Therefore, to carry out the coupling reaction, an optimum pH is needed. In actual practice, the optimum pH for such coupling reaction is between 9 to 10. B is coupling with amines. First, tertiary amines. The mechanism of coupling reaction of diazonium salt with tertiary amines is similar to that of phenols, except that this coupling is carried out under weakly acidic condition. Next is reaction with the primary and secondary amine. Coupling of diazonium salt with primary or secondary amine occur in neutral or mildly alkaline medium. Here NH2 group of the amine first attack the diazonium cation to form diazoaminobenzene. However, when the diazoaminobenzene thus formed is heated in presence of acidic medium, it undergoes diazoamino-amino-azo rearrangement to form para-aminoazobenzene by the following mechanism. Next is role of pH in this reaction. In the presence of a high concentration of H positive ion, the lone pair of electrons on the nitrogen atom accepts a proton. As a result, the amine exists predominantly in the protonated form as shown below. Due to the absence of a lone pair of electron on the nitrogen atom, the amine is no longer nucleophilic and hence the coupling reaction will not occur at a high concentration of H positive ion, that is low pH. Further, as explained above, too highly alkalinity will also not favor coupling reaction by forming unreactive diazo hydroxide or diazotate salt in significant amount. Therefore, an optimum pH of 4 to 5 is employed for such coupling reaction. So here we complete our chapter. So let's take a overview on the summary of this chapter. पहले हमने पढ़ा डाइएजोटाइजेशन क्या होता है, उसके बाद डाइएजोटाइजेशन जब हम करते हैं तो 1 मोल ऑफ अमाइन रिएक्ट करता है विद 3 मोल्स ऑफ मिनरल एसिड, जिसमें से 1 मोल डिसोल्व हो जाता है अमाइन के साथ, दूसरे वाला लिबरेट हो जाता है HNO2 में से टू फॉर्म NaNO2, और जो थर्ड वाला मोल होता है वो हेल्प करता है प्रॉपर एसिडिटी को मेंटेन करने में, जिसको कि एसोडाई बोलते हैं। फिर हमने पढ़ा स्टेबिलिटी के बारे में, अरेन डाइजोनियम सोल्ट्स की फिजिकल प्रॉपर्टीज़ पढ़ी, फिर उसकी केमिकल प्रॉपर्टीज़ हमने पढ़ी, जिसमें सब्स्टिट्यूशन रिएक्शंस हमने देखी, जिसमें सेंडमेयर रिएक्शन, गटरमैन रिएक्शन, बाल्सकाइमन रिएक्शन, गोमबर्ग रिएक्शन एटसेट्रा हमने पढ़ी। फिर हमने कपलिंग रिएक्शन को देखा और रिडक्शन को देखा। सो दिस इज़ ऑल अबाउट दिस चैप्टर. Thank you all for this chapter. I hope you will understand this.